JET, the Joint European Torus, is the world's largest experiment into fusion as a source of energy. Fusion is the process by which the Sun, with its central temperature of 17 million degrees, generates energy by fusing hydrogen atoms together. In the building to the left of the rising Sun, JET routinely achieves a central temperature exceeding 100 million degrees. This aerial view shows the JET building with its characteristic projections on the roof. This design provides space to raise the vertical double doors which divide the building into a service area and a torus hall. When the doors are raised, a crane can pass between the two halls. Inside the building, we travel with this crane from the service area past the massive concrete walls into the torus hall. This is JET, an experimental machine known as a tokamak, in which the necessary conditions of a sufficiently high density and temperature are achieved by containing the hydrogen using strong magnetic fields inside a large vacuum vessel shaped like a ring donut. The hydrogen gas inside is heated to the high temperatures required by fusion and forms a plasma, a mixture of positively charged nuclei and negatively charged electrons. The magnetic field also protects the vessel's walls by isolating them from the hot plasma. A special video camera system has been devised to view the plasma during each experimental pulse, which lasts about 30 seconds. The video camera sees a view similar to this photograph, and the actual view is shown here. We are now in the control room, where we are going to see the preparations for a pulse, followed by the pulse itself.
Right, we're getting close. I think we can wind up the generators then, Jerry. Beams will be another couple of minutes. You're already up to speed. Start when you like. Which best? We'll wait till this. 2 minutes, Peter.
The engineer in charge of the session is responsible for the safety of the machine and ensuring that all the vital systems and diagnostics are ready before he triggers a shot.
Okay, John.
Many teams and individuals are involved in this preparation. The physics team, with a physicist in charge assisting a session leader, is responsible for the experimental program for the particular session.
Okay, Peter.
The flywheel generators store the energy required to provide the magnetic fields for the shot and reduce the demand on the supply grid to an acceptable level. The local power station at Didcot is able to inhibit the shot if there is any supply problem. The countdown is automatically stopped at 30 seconds to allow the engineer in charge to make a last check that everything is ready for the shot.
ABN 37682 started. 2 minutes.
Having confirmed that all is ready, the shot is restarted, and at time 0, currents start to flow in the magnetic field coils, followed by plasma formation 40 seconds later.
Are you saying that?
Because in this pulse it is also, we don't use the beam there.
682. How long is the flat top that they can do pellets?
Leaving at 30 seconds.
Right, we're just waiting for the generator to come up. And then we can trigger.
Okay. Okay, John.
Okay, Peter. Beams are happy. Power supplies. Okay, let's trigger then. We're now in the last 30 seconds of countdown.
Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1,
The
0.
klaxons sound a warning as currents begin to flow in the magnetic field coils. Preparations continue for the shot. The plasma is now forming, and the plasma current increases to several million amps. This view of the plasma is displayed on monitors in the control room, so that the operators can see immediately if the plasma has behaved as expected. It can also be replayed, and is a valuable aid in determining the cause of any deviations from the expected behavior. Before replaying the pulse, here is an explanation of what you have seen. In this static view taken by the video camera, you can see some of the important components of the vessel. The light you see during a shot is caused by interactions of the cooler ions at the edge of the plasma with these components. The core of the plasma is so hot that it emits most of its radiation as X-rays rather than visible light. The plasma starts with a circular cross-section which touches the inner and outer rows of protection tiles, which are made from carbon-reinforced graphite, a material which can withstand high heat loads, which is used, for example, as brake linings for racing cars and Concorde. The plasma current increases to a value which is typically 3 to 5 million amps, but for this shot it is 4 million amps. The plasma shape is then changed by altering the magnetic fields to what is called the diverter configuration, because the plasma is then in contact with the diverter, a continuous trough-like structure at the bottom of the vessel. The specially shaped graphite tiles in the diverter can withstand a total energy input equivalent to 100 megawatts for a few seconds. With the plasma in this shape, the additional heating by radio frequency antennas and by neutral beams is applied, and the plasma core reaches typically 100 million degrees centigrade. The conditions at the edge of the plasma in contact with the diverter also change, with an increase in power and emitted light. The pulse will now be replayed. On the right-hand side will be shown the additional heating power. The current in the plasma increases. The shape changes to diverter configuration, additional heating on, and you will see that the increased light from the diverter coincides with the additional heating. Additional heating off. The shape then changes back to the circular cross-section, and the current is gradually reduced to zero. Clearly, if fusion is to be a source of energy in the future, it is necessary to produce energy in a usable form, and to produce much more than one consumes in the generating process. In jet, using a mixture of the two hydrogen isotopes deuterium and tritium as fuel, more than 11 megawatts of fusion power was produced. This approaches the balancing of the input and output powers. Jet has also confirmed that the fusion output from a tokamak scales strongly with machine size. The next step, therefore, is to build a bigger machine, which will run continuously, producing much more power than is consumed. This project will also test the system plan for converting the energy of the fast neutrons produced into heat, which can be used to generate electricity. This machine is called ITER, the International Tokamak Experimental Reactor. JET is uniquely able to provide the plasma conditions relevant to this machine, and an important part of the future JET program is to provide data to assist in the design studies for ITER.